Okay, so this video will look at the definition of central limit theorem and illustrate it with like a bunch of examples. Okay, so what is the central limit theorem? So this I'd like to state that this is one of the most important theorems in probability and statistics. Okay, so most important theorems. And the proof of this is actually beyond the scope of this course. It involves a fair amount of work. So at least if you would like to do this in general. Right, so what is a theorem? So what it says is that if you have x1, x2 up to xn being IID samples from any distribution, okay, D, and with mean mu, variance sigma squared, okay, so you need the mean and the variance to be well defined. Then the distribution of this new variable, which is the empirical mean minus the mu, okay, which is like the mean of the distribution, divided by sigma by root n. Okay, so this shows up because of some computational reasons. Okay, so sigma divided by root n. This distribution converges to a Gaussian with mean 0 and variance 1. Okay, by converges to, I mean as n increases. Okay. First sight, this seems like a very weird theorem, right? So it's talking about, it's looking at these, you have a bunch of samples, and it's talking about the mean estimator, which is x1 plus x2 up to xn divided by n. And it's talking about this other estimator, which is like t minus mu divided by sigma by root n. Seems a bit weird, and it's saying that this converges to n01. Okay, or let me plot it with some graphs so that you at least know the exact meaning of this, and then we'll come to the interpretation. Okay, so what is so let me give you a bunch of examples. Okay, so I started out with the distribution D being the uniform over 0 1. Okay, or yeah, over 0 1. Okay, so that mu is half, and sigma squared, and sigma squared is some constant. I don't remember it off the top of my head. It was like 1/3 or something. Okay, so this is what we started off with. Okay. And now I am plotting in this figure this random variable, which is t minus mu divided by t minus mu, y I am defining it to be t minus mu divided by sigma by root n. Okay, and this is what happens. So if n equals 1, t is like just taking, if n equals 1, t is equal to x1, right? So it's just like taking one sample, and then I'm just plotting x minus 1, x minus half divided by sigma. Okay, and this, as you would expect, is simply x minus half. If x was uniform in 0 1, x minus half is uniform in minus half to half. Okay, and that's what's showing up here. So I am ignoring the scaling by sigma for now. I'm just setting sigma equals 1, but otherwise it would just be scaled by a little bit. Okay, and I've done this throughout in the plot. I didn't want to, like sigma is some small constant and it doesn't matter what it is, it will just scale the x-axis of this distribution a little bit. Okay, so so that's what it is, right? So in the first case, this is supposed to be a uniform distribution. Because of sampling, I got a little bit of fluctuation. Okay. But now here is n equals 2. Okay, so and that's like x1 plus x2 by 2 minus half divided by 1 by root 2. Okay. And if you think about it, dividing by 1 by root 2 is like multiplying by root 2. So, and that's what I've plotted here. This already, in fact, if you carefully work this out, this turns out to be a distribution of this kind. Okay. And now you do this for a higher value of n, let's say n equals 25. This already you see a little bit of like curvature, and this looks like a Gaussian. And if you do n equals 100, this becomes much nicer. This becomes basically like samples from a Gaussian. Okay, and this is what the central limit theorem tells us. Okay, that if you take larger and larger n's and compute this parameter y, you end up being converging to a Gaussian. Okay. So what's the significance of this? We'll see that in a minute. So that was a little bit about the statement of the central limit theorem and a quick demonstration of how it works. Right, so let me now say why I said that this is one of the most important theorems in probability and statistics. So so the point is, so what is the central limit theorem saying, right? So let me write a different way of writing the same thing. Show you a different way of writing the same thing. So y is this random variable that is t minus mu divided by sigma by root n. Right, so and this is like we are saying that y, the distribution of y converges to a normal distribution 0 1. Okay, and the cool thing is that there is really no assumption on xi's came from d. There is really no assumption on what this d is. Okay, so it's just some distribution with mean mu and variance sigma squared. Okay, so take any distribution with mean mu and variance sigma squared, and you compute this thing. Okay, draw samples from that distribution, and then you compute this thing, and the distribution of this looks like a normal distribution when n tends to infinity. The number of samples n tends to infinity. Okay, and let me say why that is nice. Right, so what does this mean? Right, so this means that if I were to look at the distribution of t, okay, so t is the sample average. Right, so then this is telling us that if I look at this sample average, the distribution of t, right, looks very similar to a normal distribution of mean mu and variance sigma squared by n. Okay, so these two statements are the same. Why is that? Because if let's say t so you have y equals t minus mu divided by sigma by root n. Right? So now, and this we said that this is distributed like n0 1. That means that t minus mu, okay, is distributed as n0 with sigma squared by n. Okay. And why is this? This is because if I have a random variable, I mean if I take y and I'm scaling it up by sigma by root n, right? So I take y and let's say I scale it up by some factor c, okay, and y was distributed as a normal, so y had a distribution like this. Okay, so it is normal with mean 0 and variance something, right? So variance 1 in this case. Then if I look at y times any constant c, that would be distributed as, that's like scaling the x-axis by a factor c. Okay, and if you think about it a little bit, so that scales everything, like the mean and the variance, everything by a factor of the mean scales by c. If you look at the variance, in this case it's just expected value of x squared, so that scales, x-axis scales by c, therefore x squared scales by c squared. Okay, so that's why y times c will be distributed as n of 0 c squared. Okay, and now I'm just setting c to be equal to sigma by root n, so c squared is like sigma squared by n. Okay, so t minus mu will be its distribution will look similar to this, which means that t will look like, I'm using the word looks like in a slightly informal way, and that's by design. Okay, so t looks like n mu sigma squared by. Okay, because t minus mu was like this, and adding a mu is a constant, so it just shifts the whole distribution, so it shifts the mean and keeps the variance and everything the same. Okay, so anyway, so the bottom line is that what the central limit theorem is saying is that if I take any random variable, okay, so if I take any distribution d which has some mean mu, variance sigma squared, and I take many copies of this random variable which are like the xi's, and I look at this average, okay, this looks like a normal distribution with like a peak which is, okay, sorry, this is a bad figure, so this looks like a normal distribution around the same mean as the original one. So your original distribution could have been like very biased, it could be something like this and so on, and maybe its mean was this point. Okay, so this was d, okay, and now you take many samples from d, okay, and you average them, and this is t, which is equal to x1 plus x2, okay, and you average them, then the distribution of t looks like this. Okay, and that's a very surprising fact if you think about it, because I mean this does not look anything like the normal, right? And this looks and this is supposed to look like the normal with mean mu and variance sigma squared by n. Okay, and furthermore, this thing does not, the theorem does not depend on d, right? So it says that no matter what distribution you started with, if you take the averages, then it looks very much like a normal. Okay, so this kind of a property is what is called universality, and there are a lot of laws in probability that try to get universality kind of theorems. Okay, so and that's a nice fact. Like no matter what your original distribution was, if you take many samples and you average them, then it looks like a Gaussian. Okay, it looks like a normal distribution. And informally, this is one of the reasons why the normal distribution is that important in statistics, because if you have random fluctuations of any kind, doesn't matter what kind they could be any distribution, and you average them, then what the distribution of the average will be very similar to a normal. Okay, so if you have like lots of let's say factors that contribute to a computation of a certain quantity, and you're averaging all those factors, now each factor could have its could be independently distributed with some variation and so on, could be a random variable, but if you average them out, the distribution of your final thing will look like a Gaussian. Okay, and that's like a very nice property, and that's why the Gaussian distribution is one of the most common assumptions for distribution of errors and distribution of various quantities.